Okay, next we move on to the second part of kinetic, which is the measurement. So there are several methods that can be used to determine order of reaction. The first one is direct or integration method, followed by a graphical method, and then half-life method, differential method, and also Oswald isolation method. For studying reaction kinetics, there are two methods, which is chemical and physical methods, and also techniques, which specific for fast reaction. So these are the learning objectives that you should be able to accomplish. The first one is using that different method to determine the order of reaction, and then explaining the two different methods for reaction kinetics. Okay, since most chemical reaction occur in stages, which I have explained the Hess law, step 1, step 2, okay, the sum of the stoichiometric coefficient of the substance in reaction, means the overall reaction, will not give us the order of reaction. If you remember, I mentioned this already. Okay, so the order can only be determined through experiment. So that is why it is essential to establish the order of the reaction with respect to each of the reactant participating in the chemical reaction. And the total order will be the sum of this order. Okay, so like I have mentioned in my previous lecture, so you will have order with respect to each of the reactant involved, and the total order will be the sum of the order of the respective order of the reactants. So there are several methods which are available to determine the order of reaction. Okay, and of course the methods will need experimental data. Now let us move to the first method to determine order of reaction, which is direct or integration method. Okay, so the experimental data collected by analysis of the reaction mixture at various time interval, and then this data will be fitted into the integrated rate equation of different order, and the order of the reaction is decided by the equation of the integrated equation just now, to give a constant value of specific reaction rate constant. Okay, we have covered this in the previous lecture. Okay, this method is satisfactory for simple homogeneous reaction, but it cannot be used for complex reaction. Okay, only for simple homogeneous reaction. So this is the example of the direct or integration method. Okay, so these are the data, okay, of the composition of the nitrogen pentoxide, okay, at 60 degrees, 67 degrees Celsius, and it's a first order reaction. Okay, and you asked to calculate the rate constant. Okay, rate constant. Now the question has given the clue here, which is first order reaction. Okay, so based on the integrated formula that you should have memorized in the previous lecture, so we write the first order reaction, okay, which is this. Okay, so we rearrange so that we want to calculate for the rate constant K. Okay, so once we arrange, it become 1 over T ln initial concentration of the nitrogen pentoxide divide with the concentration of the nitrogen pentoxide at different time interval. Okay, so we insert the concentration at different time. Okay, and if the rate constant k is found to be constant, then direction is true, okay, which is first order. If it's not, mean it's not first order, but the question already mentioned it's a first order. Okay, unless the question does not mention first order, then you have to try the different integrated formula for different order of fraction. Okay, so you have to insert all these values inside the integrated formula, and whichever formula that gives constant value or the similar constant k value, then it obey that particular order of fraction. Moving on to the next method is graphical method. Okay, graphical method. So this method is very useful to determine the order of fraction. Okay, so when a suitable function of concentration is plotted against time, we will get a linear plot. Okay, so the order of fraction will depend on the nature of the function of the concentration, and the slope of that plot will give the value of the rate constant k. So the integrated general equation can be expressed as this. Okay, so this is the general equation. Okay, with respect to the reactant C here. Okay, now this is the case for zero order. Okay, for zero order, this is the formula. Okay, which is y mx plus c. So general formula. Okay, this is for zero order. Okay, k is the slope of the plot. Okay, so we plot concentration versus time, and it should give us straight line. That is for zero order. Okay, for first order, this is the formula of y mx plus c. So from here we can see that the y-axis is ln c. Okay, the x-axis is t. Okay, so we plot ln concentration versus t, and it should give us straight line. That is for first order. Okay, for second order, okay, y mx plus c. Okay, so the y-axis is 1 over concentration, okay, versus t, and it should give a straight line. That is for second order. Okay, so you have to try try and error here. Okay, using the information of the concentration and also t, we plot. Okay, so for zero order, we plot concentration versus t. If you don't get a straight line, then it does not belong to zero order. Next, try to plot ln c versus t. Still not a straight line obtained, then it's not a first order reaction. And moving on to the second order, you try plotting the 1 over concentration versus t. And if you get a straight line, then that particular reaction obeys second order reaction. And that's how you do for graphical method. So again, you have to memorize this point here. Okay, c versus t, ln c versus t, and 1 over c versus t. Okay, so this is the example of the plot based on the previous data just now for the direct integration method. Okay, so the concentration of the nitrogen pentoxide, okay, you ln it first, okay, and because it's first order, okay, versus t, and you get a straight line here. Okay, so it obeys the first order. Okay, because the the plot is straight line, and the slope of this straight line will give you the rate constant k. Okay, next we move on to the third method, which is half-life method. Okay, so the half-life for the nth order of fraction is written as this. So this is the general formula for half-life method. Okay, and so we log this formula both sides. So we get ln half-life equals ln k, okay, ln k plus this one being here 1 minus n ln a. So here A is referring, okay, here A is referring to the initial concentration. Okay, initial concentration. So actually, if you look at the arrangement here, is Y mx plus C. Okay. So here is axis x, this one is axis y. So if we plot ln half-life versus ln a, okay, so we plot here, okay, we plot, okay, ln half-life versus ln a. Okay, so it will give us straight line with different slope for different order of reaction. Okay, so if we have the slope of value of 1, okay, here, okay, 1, so this is 0 order, okay, 0 order. So if we plot ln half versus ln a, and we have a slope of 0, so like this, so this is referring to first order. Okay, just write like this, okay, first order. And if we plot ln half-life versus ln a, we get a value of -1, okay, -1. So that is referring to second order. And we plot half-life versus ln half-life versus ln a, and we get value of -2, okay, -2. So that refers to third order. Okay, so that is half-life method. Okay, so we must have half-life value and also initial concentration data in order for us to plot for this half-life method. Okay, next we move on to the fourth method, the differential method, or we call it Van Hoff differential method. Okay, Van Hoff. Van Hoff. Okay. So this order of reaction is found by carrying out the experiment twice. So we have to do the experiment twice, but using different initial concentration of the reactant, one of the reactant, okay, and then the other reactant, the concentration is kept constant, okay, kept constant. Now this is reactant 1, okay, this is reactant 2, okay. So we log and solve these two with respect to the order n here, okay, because dc over dt equals to kc1n and negative dc2 over dt equals to kc2n. Okay, so we bring these together, so we get dc1 over dt divide with dc here, okay, and then we bring this together, we get C1 divided by K, because the similar value or similar unit here is K. Okay, so kita samakan penyebut K lah for these two, so we get this expression here. Okay, and then we log. Okay, we log. Okay, so we log with respect to n here, n. Okay, so we end up getting this. Okay, ln dc1 over dt minus ln negative dc2 over dt over ln c1 minus ln c2. And the order of fraction here, n, with respect to the reactant, okay, can be determined. Okay. So the alternative, okay, of determining the order of reaction of differential method is from the slope. Okay, from the slope. Okay. So we have ln negative dc over dt and then ln c. Okay, so we plot this. Okay, we plot this. Okay, and the slope will give us the value of the order of reaction. So if the value of the slope is 1, then it's referring to order of reaction 1. If the slope is 2, then order of reaction 2. If the slope is 3, then order of reaction is 3. Okay, simple as that. Okay, let us look at the example here. Okay, so when different reactants participate in chemical reaction, the reaction order may be studied by varying the concentration of one of the reactant. Means the other one kept constant just now. Okay, so let us consider this rate equation. Okay, negative dc over dt. Okay, rate. Okay, rate equivalent to k reactant A with the order of m and reactant B order of n. Okay, so for given A and B reactants, okay, the initial rate is determined at any instant. Okay, so when B is double, let's say we double this, okay, we keep A the same, A constant. Okay, so this is how we write the rate. Okay, now we double. Okay, we double B, so it's 2B. Okay, A is kept constant. Okay, not that this is change already, because we are changing uh, the concentration here. Okay, so we divide that negative dc over dt 2 with negative dc over dt 1, so we'll end up getting 2 power of n. Okay, 2 power of n. Okay, so we rewrite back just now. So it was negative dc over dt, right? 2. Okay, k a m 2 b n. Okay, the other one just now is dc negative dc over dt 1. Okay, k a m over 2 over b n. So we divide this. Okay, we divide this. So that's why we end up getting dc over dt 2 over dc over dt 1. And here, okay, because similar, okay, so we cross this, okay. Now this is 2b, so we can cross b. Okay, b, so leaving behind 2 power of n, so that's why you get 2 power of n here. Now we rearrange so that we are finding n, so it becomes 1 over ln 2, okay, times ln dc over dt, okay, over dc over dt 1. Okay, so the value of n is the order of reaction with respect to b, so, because b is the one that we vary. Okay, we change the concentration. Okay, so we can determine the order for a, which is m just now, by doubling the a and keep b constant. Okay, next we move on to the last method to determine over the order of reaction, which is Oswald's isolation method. Okay, so this method is determined by taking a number of reactants in large excess except one. Okay, so the rate of the reaction will be dependent on the isolated reactant, or the one of lowest concentration. Remember, the remaining is in excess. Okay, except only one. Okay, for example here. Okay, so we write the rate expression. Okay, negative dE over dt, KAL BMCN. Okay, so L here can be determined using this method here, in which reactant B, reactant C is in excess. Okay, remember I mentioned pseudo first order. Pseudo is when it involve reactant in excess. Okay, so we cannot consider it in the red law expression. So when B and C is in excess, so we are determining the red law of the order of reaction for reactant A, which is L here. Similarly, we can do it for B and also C. So if we want to determine B, okay, order with respect to B, dB over dt. Okay, so K A L B M C N. So to determine reactant B, which is the order M, A and C is in excess. Okay, so we can find the order with respect to B. Okay, we can do the same for C. Okay, and the sum of these L, M and N is the overall order of the reaction. So that is Oswald isolation method. Okay, next we move on to method to study reaction kinetics. Okay, so there are two broadly defined goals. Okay, the first is to characterize and confirm details of the mechanism involved in complex chemical processes, and these include dependence of the reaction rate on concentration and temperature, identity of all species present or involved in the reaction, or the extent of reaction. And second goal is to study the kinetics of the individual elementary reactions. So I have explained to you what elementary reactions is. Okay, so this study of the kinetic will provide the rate data for elementary steps which are required for assessing complex reaction mechanism. So what are the techniques used to study kinetics or to measure kinetics? So the experimental methods in chemical kinetics are characterized by these three features here. The first one is method of initiation, followed by a suitable medium in which a reaction may take place. And the third one is method of detection. So we look first at initiation methods. Okay, so before a reaction can take place, the reactant molecules must be activated, okay, in order for the reaction to proceed. Okay, and how to activate the reactant molecules? It has to be induced, okay, to a minimum energy, okay, so that the reaction will begin. Okay, so there are various methods for initiation. Okay, either by thermal activation. Thermal activation means heating. Okay, heating the reactant molecules from 300 to 3000 Kelvin, or we initiate, okay, the reaction by electrical discharge using microwave and also radio frequency Okay, and these are the frequency, okay, of the electrical discharge in order to induce, okay, the reaction. Another approach is by chemical activation, okay, which is photo activation. Okay, so photo activation is a photochemical reaction which is initiated by absorption of light. So involve light here. Okay, at lambda 120 to 700 nanometer. Next, we look at system. Okay, kinetic system. So there are two system. Okay, the first one is static system. So static system is a closed constant volume container, okay, which serve as the measurement medium. Okay, so this is step 2 just now. Okay, suitable medium in which reaction take place. Okay, so the medium can be a static medium, okay, or a flow medium. Okay, so static means a closed, okay, closed constant volume. Okay, so there is usually a finite time required for the reactant to fill up the vessel, okay, and then mix with each other, okay, and then reach equilibrated temperature. Okay, so the limitation of mixing time, okay, is overcome by initiating the reaction using electric discharge or pulse light. Okay, so the product immediately after this initiation by electrical discharge or pulse light will be observed, okay, by time resolved spectroscopic detection. Okay, the third one, the third method is now detection method. So the next type of kinetic system is flow system. Okay, unlike static closed system, flow system is an open system. So means reactant constantly entering and then product constantly leaving the reaction zone. Okay, so reactant sentiasa masuk, produce reactant, produce product keluar. Masuk lagi reactant, produce product keluar. Okay, it's continuous. Okay, the advantage of this flow system is that the processes proceed at moderately fast rate can be measured. Okay, the principal requirement for this flow measurement is a steady non-turbulent flow. Okay, so the flow has to be steady, not non-turbulent. Okay, otherwise it will disturb the reaction rate. Okay, the kinetic rate. Okay, this is to ensure we have a stable concentration distance profile. Okay, and then series of measurement can be made along the flow tube. Okay, so that is flow system.